Hi everyone. So today we're going to take our conversation from geometric sequences to exponential functions. So our focus today is going to be on a new type of function, and our objectives for today are going to be to evaluate exponential functions and to identify and graph exponential functions. Okay, so to start things off, let's look at what an exponential function looks like. So an exponential function has the form f of x equals a times b to the x, where a and b are numbers that don't change, and x is some variable that we can plug numbers in for. So in this form, a does not equal 0, b cannot equal 1, and b has to be greater than 0. So let's think back to our previous lesson on geometric sequences. So you remember this form, a sub n equals a sub 1 times r to the n minus 1? This actually looks really similar to our new form of exponential functions. If you look here, a sub 1 is really like a here, r is like b, and our ratio never changes. And n minus 1, that n term is the thing that can change. So the x up here is the thing that can change for us. And that will give us our function evaluated at some x, or in other words, whatever term we were looking for. Okay, let's think big picture for a minute. We're not just learning exponential functions because we want to. We're learning them because they're useful and because they differ from other functions that we've seen before. So we've seen three types of functions. We've seen linear, we've seen quadratic, and we're about to see exponential. So let's compare some aspects of these to each other. Let's look at equations first. So with linear, we had three different types of equations. We had standard form, we had slope-intercept form, and we had point-slope form. With quadratics, we had some form where x had to be squared. That was the big idea with quadratics. With exponential functions, x is in the exponent. So our variable changes in the exponent. Now let's look at differences in ratios. So if we're given a table of values, how do we tell different functions apart? Well, with linear, we added or subtracted a constant term between any terms. So here we have like plus 2, plus 2, plus 2. In quadratics, our second differences were the same. So our first differences here, like plus 1, plus 3, plus 5, are not the same. But if we look at the second differences, plus 2, that's quadratic. For exponential functions, we don't want to add or subtract anymore. We're looking at common ratios, so we want to multiply. So here, between terms, we have something times 3, and then times 3 again, and then times 3 again. That's our common ratio. Now let's look at graphs. So with linear, we had lines. They were straight lines. Some look like this, some were horizontal, some were vertical. With quadratics, we had parabolas, either upward facing, downward facing. They could be stretched or compressed. And with exponential, we have graphs that look like this. Now I know we haven't seen this before and we'll work with it, but this has a gradual slope upwards, and it keeps going upwards more and more quickly. Alternately, you could have ones that go downwards, or you can even have them flipped over the x-axis. But we'll see some of those in a bit. Say our objective is to identify an exponential function. We can do this by analyzing the ratios between terms. So we've been used to seeing functions where the y values only increase by adding or subtracting. Here, we're going to be looking at the y values being multiplied by some factor. So let's learn how to do that. Let's see if we can figure out whether these functions represented here are actually exponential. So let's look at the first one. As x increases or decreases by a constant amount, y has to be multiplied by some term. So here, x increases by 1 each time, so we're good. Y, we're going to have to divide one term by the one before it. Does that sound familiar? It should, because that's what we did when we were making geometric sequences. So we're going to be dividing 3 by 1.5, 6 by 3, and 12 by 6. So let's do this one first. 3 divided by 1.5 equals 2. So 1.5 times 2 equals 3. 6 divided by 3 is also 2, and 12 divided by 6 is also 2. So here, we're multiplying by 2 each time to get our next term. This one is exponential because that ratio stays the same. So yes, this one is exponential. Let's look at number 2. So number 2, x still increases by a constant amount. Here we're going up by 2 each time. And let's look at y. So here we're going to take a term and divide it by the one that comes before. So we have 5 divided by 1, which equals 5. How about the next one? 10 divided by 5 equals 2. And 30 divided by 10 equals 3. So our ratios here are not the same. We have 5, we have 2, and we have 3. This one is not exponential because we need those ratios to be the same each time. So no, this one is not. Our next task is to graph. So what do we want to do? We want to graph an exponential function. How are we going to do this? The same way we've always made graphs. We're going to make a table of values and we're going to plot points. So the great thing about exponential functions is that you don't have to do all the work to figure out what numbers are going to go in the x column. We're pretty much going to be centered around 0. So you want 0 to be somewhere in the middle here. I'm just going to pick -1, 0, 1, and 2. And that should give us a pretty good idea of what our graph is going to look like. Now y I'm going to find by plugging points into my function, which happens to be y equals 4 times 3 to the x. So I have a times b to the x. All right, so let's do this. When we plug in -1, we're going to get y equals 4 times 3 to the -1. And this is going to be 4/3, or about 1.3. So 4/3. And if I plug in 0, I'm going to get 4 times 3 to the 0, and anything to the 0 power is 1. So 4 times 1 is 4. If I plug in 1, I'm going to get y equals 4 times 3 to the 1, and 4 times 3 is 12. And if I plug in 2, I'm going to get 4 times 3 squared, so 4 times 9, which is 36. All right, let's graph these. So we have 1 point, -1 and 4/3. 4/3 is about 1.3. So -1, 1.3. And if you'll notice, I counted my y-axis here by 2's because exponential functions get really big really fast. They grow exponentially. So we're going to need a lot of terms on here. And we might not even be able to fit them all. So we plotted 1 point. All right, let's go to 0, 4. So we have 0 and up 4. And then we have 1, 12. So 1 up to 12. And then we get to 2, 36. So 2, 36 is going to be like double the length of what I have right here. So I have 2 and then something way up here. So let's connect these lines and see what it looks like. Connect these dots. We're going to get something that looks like this. Ooh. So something that gets really gradual over here, a really small slope, and then all of a sudden increases really fast, right at 0. This is what an exponential function is going to look like. Let's see what another one might look like. Here our function is y equals 3 times 1/2 to the x. So again, we have a times b to the x. So we're going to make our table pretty similarly to before. We're going to have 0 somewhere in the middle, and I'll just start at -2 this time. So -2, -1, 0, 1, 2. That should do it. So now we're going to plug in these points into our function and find y. When we plug in -2, we're going to get y equals 3 times 1/2 to the -2. 1/2 to the -2 is actually 4. So 3 times 4 is 12. When I plug in -1, I get y equals 3 times 1/2 to the -1, and that's 3 times 2, so that's 6. When I plug in 0, I'm just going to get 3, since 1/2 to the 0 is just 1. And you should be able to notice a pattern so far. Do you see these y values? We're going from 12 to 6 to 3. 12 divided by 2 is 6. 6 divided by 2 is 3. 3 divided by 2 is 1.5. Let's see if we get that when we plug this in. So y equals 3 times 1/2 to the 1. That's going to give us 1.5. And if we plug in 2, we're going to find that we'll get 0.75. All right, let's graph these. So you can see that our y values here are a geometric sequence with a common ratio of 1/2. All right, so if I graph this, I'm going to start at -2 and go up to 12. Again, here I have my y-axis going up by 2 so that I have enough room. So -2 up to 12, point right there. I'm going to end up covering up my work here. Maybe I'll just erase it for now. So I'm going to go up to 12, and then my next point is going to be -1, 6, so right there. At 0, I'm going to be at 3. At 1, I'm going to be at 1.5, which is almost a 2 here. At 2, I'm going to be at 0.75, which is a little bit lower. And now you can see that I have a gradual progression downwards. So if I connect these points, I'm going to have something that looks like this. This is like the opposite of what we saw before. It's just flipped this way. It's flipped over the y-axis. So now I have something going downwards. Now, we're not going to explore the exponential functions that are flipped over the x-axis, but you'll see them later on. All that happens is that it looks the same, but it's below the x-axis. All right, with that, I will leave you to try the problems at the bottom of your guided notes, and thanks for watching.